Hello, my name is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar on what's new in SigmaXL version 9. This is part 1, new and improved control charts, part of a 3-part series webinar. In part 2, we will do time series forecasting, and then part 3 will be control charts for autocorrelated data. So for today, we have new and improved control charts. We will talk about the templates, rare events, T, G, and probability-based G, trend and toolware, exponentially weighted moving average, tabular Qsum, cumulative sum. We'll look at average run length calculators, in particular Shewhart and EWMA. For time, we won't be able to cover all of these. And we will cover some of the improvements that we've made in the test for special causes and some of the dialog updates and menu updates. The format will be 45 minutes for presentation and then 15 minutes for question and answer. Please type in your questions. Because of the number of participants, we can't have the microphones turned on. So I just ask that you type in your questions, and then at the end of the presentation, I'll review those questions. So I'll launch into the presentation. Oh, and also to mention, the PowerPoint slides that I'm using will be available for download after, as well. The data sets and the examples come from the SigmaXL workbook, so you'll be able to reference that. And the webinar itself is being recorded and will be available in a couple of weeks after the presentation. So with that, we'll start with the rare events T chart. The rare events T and G charts are primarily used in healthcare. The T chart is a time between chart, is an alternative to the standard attribute chart when the adverse event of interest is relatively rare and a measurement of time between each occurrence can be obtained. If the rate of occurrence follows a Poisson distribution, then the times between will have an exponential distribution. And so what is done here is an approximation is made by transforming the time measure to the 1/3.6 power. That turns it into a symmetric distribution. Shewhart is applied to the transformed data, and then the control limits are calculated on the inverse transform. This actually comes out of the Provost and Murray book, Healthcare Data Guide, Learning from Data for Improvement. It's popular in healthcare, and so we're following their guidelines here for the control limits. So basically, you'd raise to the 1/3.6, calculate the moving range. There's an outlier screen they include, and then you compute the control limits, and then you come back and you transform back to the original units. So it's pretty straightforward, and it's a way of accommodating these rare events that often occur in healthcare. And so the first example will be days between surgical site infections. And so I will go into the new templates that cover the rare events. So first of all, switch over to Excel. And the templates, by the way, are available under Templates and Calculators, Control Chart Templates. The new ones are rare events, time-weighted, trend, and the average run length calculators. Or under control charts, control chart templates. They're the same, it's just two different ways to get to them in the menu. So if we go rare events T, that brings up the template. And just to point out, what you typically do is you populate the date in column A, and then we just have a simple formula that takes the difference between the cells, cell 3 minus 2, 4 minus 3, and so on. So it just does the calculation, the days between calculation for you. So what I'm going to do is I'm going to get the example, which is days between, And what we have here are days between before improvement and after improvement. So an important part of these types of control charts is that you want an out of control signal on the upper control limit. That's an indicator of an improvement because it means that the duration is increasing. So you're actually, so by increasing the time between, you are reducing the number of adverse incidents. So here I'm just going to do Control C, and I'm going to paste in. I'm going to do paste values so I don't change any of the formats. But as you can see, it just calculated the days between. And then all I do is I click Rare Events T Control Chart, and there's my control chart, and we're in control as expected. Now, we implement an improvement project, and we're hoping to see the time between increase, significantly increase. So I'll go back here, and now I'll take these dates for the after, copy, and paste values. What I want to do now is I don't want to recreate the control chart because that'll calculate the control limits with all the data. I want to use the control limits that were calculated on the original data, and I click Add Data, and so the control limits are the same. It rescales, but the control limits stay the same, and we confirm here with this T-chart that indeed the process has been improved. After 20 or 30 data points, you would probably want to use just the new data to recalculate your control limits. Okay, so it's pretty straightforward. It's a template. Just copy and paste and create your chart. And then when you have enough data, 20 to 30 data points, then you use Add Data and you just continue on that way. So that's the T chart. Next, we'll look at the G chart. So the G chart, or geometric chart, is an alternative to an attribute chart. Again, the adverse event of interest is rare, but this time there are discrete opportunities between events that you're counting. So the control limits are shown here. This is again out of Provost and Murray. I'm not going to go into the formula details, but basically it models a geometric distribution. And now it is an approximation. I'm going to show you a better chart in a moment called the probability-based G chart, but this is a popular chart because it's quite simple. And we will use doses dispensed between adverse drug events for the example on the G chart. So to access the G chart, I go SigmaXL, Control Charts, Templates, Rare Events G. And again, in this one, it does the same thing that if you use date, if you want to make the item to be charted as days between, this will also work. But in this particular example, we're going to use doses dispensed between adverse drug events. Again, we have a before improvement and an after improvement. So we have a date and we have doses between events. So I'll copy that into the template. Again, paste values. I will create, so by doing this, it overwrites the formula the difference formula, that's fine. Because we actually have the doses between events that we're using. And we create the G chart. So it's in control. In control isn't necessarily a good thing. It just simply means the process is stable. So again, as with the T chart, you would like to see the process out of control on the upper control limit because that means there are more doses between adverse events. So we will now go back and I'm going to now take the after improvement data, copy that, put that into the template, and I'll do paste values. We can just make this a little wider to see the dates. And I want to add data, again, because I don't want to recalculate the control limits. I just want to add to the existing chart. And we have an out-of-control process, which is good. That's what we want. This is confirmation that the process has improved and that the doses between events are significantly higher with the new process. Now, I mentioned that the G chart is an approximation. We have something called a probability-based G chart. And it's a little more theoretical, but again, the template takes care of the math. What the user has to do in this case is you specify the type 1 false alarm error rate on the upper control limit. And the formulas are given here. I'm not going to get into the details, but basically you specify the alpha and it'll work with that and compute the control limits from that rather than using the approximation formulas, the Murray-Provost approximation formulas. So here we'll use the same data and we'll run the probability-based G chart. So I go back to SigmaXL, I go control charts, control chart templates, rare events prob G. So you'll notice it's the same thing, but now the other thing you can do is if you have a known event probability, it will use that to create the control chart. We don't have that. We just have our baseline data, which will then actually report the event probability as well. So I'm going to copy and paste the doses dispensed between before improvement. And again, I'll paste values. I'll create the prob G chart. I'm using an alpha of 0.00135. This is the same alpha that corresponds to a Shewhart chart, upper control limit, one-sided probability upper control limit on the Shewhart chart. If you're willing to accept a higher risk, you can change that to 0.01, and that would give you an average of 1 in 100 false alarms. So I'm just going with the traditional Shewhart chart, but with this one, you can actually adjust the alpha, and that'll adjust the control limit. So I'm going to click the rare events prob G chart, and here we go. Notice it tells us that the control limits were calculated using 20 data values, and it gives us the event probability. And then if you wish, you can actually use that and type that in. But if you use add data, we'll use this event probability automatically. So we'll now add the after improvement. And we'll copy that, paste that into the template. Again, make that a little wider and add data. Okay, so when I use the prob G chart, notice if I switch over to the G chart, you see they're more out of control. And here we only have this 1 point. So the limits are wider, but the difference is that the limits are correct, statistically correct. But as I said, if you want, you can actually go back and you can adjust the alpha, and it will, in this case, if I changed it to 0.01, it would lower the control limit. But we still see that indeed this process has been improved. Okay, so that's the rare events charts. And as I mentioned, every example that I'm going through is in the workbook. So anything that you wish to reproduce, you can look at the workbook, and all the data sets are under sample data. Next, we're going to look at the trend, also known as toolware chart. The center line for this chart is a linear regression equation. So basically what you have is a positive or linear trend that is inherent to the process. And what we do is we do a regression equation and then build the upper and lower control limit to track the linear regression equation. It's important to note that you need to have a good linear regression model. R-square should be at least 50%, preferably greater than 80%. And the point is that the model estimation error is not included in the control limit calculations. We're just basically using the residuals of the linear regression model. So the assumption is that you have a good linear regression model. It's really not appropriate for a situation where you have a weak. In fact, something like that would be better to use exponential smoothing, which we'll talk about in the next 2 webinars. Tool wear is a classical example where there's a slow and gradual change in the tool dimension due to wear, and it's well known, well characterized, and you want to control chart it. But if you were to just use a regular control chart, you'd have false alarms all over the place. It's just not usable. So by using the trend chart, you take that trend out. So we'll use a trend chart example, and that's just called trend chart example. Switch over to trend chart example and grab that data and open up the template. So control charts. So now I'm going to trend. Again, I'm going to paste the data, create my trend control chart. So as you can see, it's a trend, and the upper and lower control limit track. And the formula for the center line is given. R-square is given here, so we've got a good R-square of 96%. This is good for this type of chart. Now, what we will do is we will add data. So I'll grab that additional data from 21 through 30 and then add that to the control chart. Again, I'll do my paste values and I'll do add data. So now we can see that the process has shifted. It is out of control. If I were to take this data and use a regular control chart, basically everything would be out of control. It wouldn't be usable. So by taking the trend into account, again, this is only applicable in a situation where there is a known trend, and that's an inherent part of the process. It's something that you just simply want to account for. Now, there is another way of doing this. If you want, you can do a linear regression and then do an individual's chart on the residuals. So you could use regression analysis. But this is nice because you actually get the residuals. When you control chart the residuals, you're not seeing the actual data. So when you do it this way, you can actually see where the data is in addition to the assignable causes. So you have an assignable cause here based on the trend control chart, and you want to take corrective action. So this is, again, a nice template. And the formulas are also given in the Provost and Murray book. Okay, so that takes care of the basic charts. Now we're going to move on to the exponentially weighted moving average, or EWMA. So the EWMA chart uses weighted averages where the weights decrease exponentially as observations come from further in the past, with the smallest weights associated with the oldest observations. And this is the formula for the EWMA statistic. And you have a lambda, or a weight, and depending on the value of that lambda determines how the historical data is weighted. It also affects what are called the average run length performance for the control chart. Later, we'll talk about the average run length calculators so that we'll be able to see what adjusting this lambda value does in terms of average run length, and that is duration to detect a shift and false alarm rate. If I have a lambda of 0.2, you can see that the weight changes rather slowly with respect to the older data. If I have a lambda of 0.8, it drops off quite rapidly. So basically, as lambda approaches 1, you essentially turn this into a Shewhart chart. As lambda approaches 0, it becomes more like a cumulative sum chart. Well, we also have the cumulative sum chart as well, but this is just to give you a feel for how this EWMA works. Now, you might ask, well, why would I bother using such a complicated formula? Because now I'm no longer going to be looking at the original data. And there are two reasons. One is because it is sensitive to small changes in the process mean. So you have rapid detection of a small shift in the process. Works much better than the test for special causes. And secondly, it's quite robust to the assumption of normality. So even if you don't have subgroups, which is what you need in a Shewhart chart to get robustness, the EWMA has built-in robustness because of this weighting. And we'll be able to see that when we look at the average run length calculators. So it is more complicated. It is non-intuitive because the plot points are no longer in the original units that you're familiar with. But what you have is a very powerful tool that can rapidly detect a small change in the process and something that is quite robust to departures from normality. The formulas are given here. I'm not going to get into the details other than to point out that the limits are moving and then they settle out, and you'll see that. And what that does is that improves our sensitivity to early departures or to early shifts in the process. Okay, and this is covered well in Montgomery book, the Montgomery textbook, which I reference here. And the references are at the end of the PowerPoint slide as well. They are in the workbook. So let's now use data that Montgomery put in his book, simulated data that's quite nice so that we can replicate the textbook example. And what I'll do there is, first of all, I'll open up the template for EWMA. So I will go control charts, control chart templates, time weighted, EWMA. So you are prompted for your weight. Now, K is the multiplier. In a Shewhart chart, you're always using 3 sigma, plus or minus 3 sigma. But in an EWMA chart, this is a parameter that can be adjusted. And in fact, typically, the settings we have here is the defaults 0.1 and 2.7 are used. Both of these affect the average run length characteristics. And we'll see that in the calculator, exactly how those affect the performance of the chart. I'm going to copy and paste from the Montgomery data. So I have, in this data, I have simulated data with a process mean of 10 and a standard deviation of 1. So I'm going to copy that into the EWMA template, paste it in. One of the things I'm going to do here, because I know my historical mean is 10, my standard deviation is 1, I'm going to put those in as known parameter values, and then I'm going to run the EWMA control chart. And we can see here that we have a process that's in control. Now, as I mentioned, the one thing, of course, that makes this somewhat of a disadvantage is because you're no longer plotting the original data points as you would in an individual's chart. However, we have a small shift of only 1 sigma. And so if I go back here and I now paste the shifted data and I add data, we see here that we were able to detect that shift, rapidly detect that 1 sigma shift. So 1 sigma is a small shift. 2 to 3 sigma. Shewhart is better for rapidly detecting large shifts in the process. So if you're more interested in large shifts, then Shewhart is a good tool to use. EWMA and Qsum can both be tuned to detect large shifts, but typically the small shifts are what we're interested in. So this is the EWMA chart. If I go in and I do the same thing with a Shewhart chart. We have the basic Shewhart individuals chart, and I'm going to repeat what I did. So 1 to 20. Now with the Shewhart chart, I don't have the ability to specify a parameter, but we'll just compute the control limits based on the historical data. So this is what we have. And then if I add the shifted process, paste that in, and I add data, you can see that the individual's control chart did not detect the shift in the process. Now, we could have used test of special causes. I'm not going to do that. That would require the use of the menu-based individual's control chart, but the EWMA and as well the Qsum rapidly detect the small shift. You can kind of see here 9 above would trigger, but there are problems associated with all those tests for special causes. So we'll look at that in just a bit. So now, that's the EWMA. The Qsum, the cumulative sum, is similar to the EWMA. It's really designed to detect small shifts in the process. The classical Qsum is called a VMask, but we don't use that. We use what is called the tabular Qsum, and that just looks more like a regular control chart. Here are the formulas. Again, we'll skip those. There's also something called a fast initial response that allows you to detect if there is a change early in the process. And for this, we're going to run the Qsum with the same data. So again, I'll go to the Montgomery data, and we'll copy that in, and I'll open up the template for the cumulative sum, and I'll paste that in. Now, I'm going to put in my target of 10 and a historical standard dev of 1. K and H are the Qsum parameters. So these are tunable parameters that affect the average run length. So typically K is 0.5, which means you'll be able to rapidly detect a 1 sigma shift. H can be 4 or 5, and you can adjust that depending on what you want in terms of your control chart performance. And we'll see that when we look at the templates. So now I'll create the tabular Qsum chart. And as you can see, the process is in control. And now I'll add the same shifted data that we saw earlier. And I'll paste that in and add data. And we see that we rapidly detect that small shift in the process. So Qsum versus EWMA is really a matter of preference. Some people prefer the Qsum, some people prefer the EWMA. They both can be tuned pretty well to match each other. EWMA is a little more robust to departures from normality, so that's a good thing. My preference personally is EWMA, but a lot of people like the Qsum chart, so both are available. So with that, I'm going to now move on to the templates for average run length. So average run length is basically says, on average, how long will it take me to get a false alarm? The process is in control. How long on average will it take before I get a signal, type 1 false alarm? And you want that number to be large. For Shewhart, it's quite large. It's 370 for a classical Shewhart control chart. Then if the process changes, a shift in the mean, the average run length for that should be small, because you want to be able to rapidly detect a shift in the process that is an assignable cause. The actual calculations are quite complex. We use either exact Markov chain or Monte Carlo simulation, we won't be getting into any of those details. The calculators take care of the details. A couple of notes on Monte Carlo. If you run 1,000 replications, it's less than 10 seconds, but you'll get about a 10% error on your average run length. If you use 10,000, it takes about a minute, and you get an error of about 3%. If you use 100,000, it takes about 10 minutes, and you'll get an average run length error of about 1%. We don't recommend using more than 100,000 replications, because then you can possibly run into memory issues, and besides, 1% is pretty good for any estimation for control chart design. So with the EWMA or the Qsum charts, we typically set the parameters to minimize the ARL1, which is the ability to detect the small shift in the mean. Shewhart, on the other hand, is very good for rapidly detecting a large shift in the mean. The problem, if you add test for special causes, that does improve the small shift performance, but then you get a very high false alarm rate. So you can, of course, use subgroups. If you have the ability to do subgroups, then you're into the next bar chart. And subgroups will give you improved sensitivity to small shifts in the process, and as well give you robustness to non-normality. So always, and then the advantage of that is that you're in the original units. You're not dealing with transformed units. But in a lot of cases, you don't have the ability to draw subgroups. You're dealing with individual observations for your control chart. And that's where the Qsum and the EWMA can be very useful if you're interested in small shifts. Just some technical details on the templates. We're assuming the parameters are known. So that's practically unlikely that you'll ever have that situation where you have actual known parameters. But for purposes of comparison, if I'm comparing Shewhart to EWMA using these templates which have known parameters, the comparisons are valid. I'm comparing apples to apples. So even though the actual run length characteristics, if I take 20 to 30 data points and I compute the control limits, there's added uncertainty due to the sample size as opposed to known parameters. So just to keep that in mind, and it also assumes that the change is immediate, and how long does it take to detect that immediate change in the process. Okay, so that's just some comments. So with the Shewhart chart, what we can see here is that we have, with a shift in the mean in control process, we have an average run length of 370, and if the process shifts 1 sigma, the average run length is 44. So it's not particularly good. If we go to the exponentially weighted moving average, and we look at the in control average run length, we have 356. And then with a 1 sigma shift, we have 7.54. So basically, you have roughly the same in control average run length, but a much better ability to detect a small shift in the process. So that's using the EWMA. This is the settings, the default settings when you open up the template. Qsum gives you, again, similar rapid detection of 1 sigma shift. In this case, with the settings, we have an even lower false alarm rate, 465. You can tune the parameters, and that will allow you to adjust the various average run length characteristics. Okay, so I'm going to move on to other changes in the software. So we have support for tests for special causes that include now the moving range, varying subgroup sizes, and historical groups. As well, if you are on individuals moving range charts. You will see now the out of control points on the moving range with the test for special causes. Tests 1 through 4 are shown. If you have an attribute chart, like a P chart with moving control limits or moving varying subgroup size, again, you get your test for special causes, whereas previously you weren't able to do that. If you had varying subgroup size, you would not be able to run your test for special causes. Other changes include the dialog. If you have in the test for special causes defaults, in this default dialog, test 1 is hard-coded. You can't uncheck that. That's always included. And then just the notes are changed to include moving range, and standard deviation charts that run tests 1 through 4. Then the menu update for individual moving range, and individual moving range S, IMR S, IMRR. These used to previously be under the advanced menu, and these are now shown under the control chart menu. So that concludes my presentation, and I will take any questions now. So if you have any questions, please go ahead and type them in. So I have a question, where can I get the workbook from? When you install the software, you have access under the help menu, you can access the workbook, PDF workbook. And I have a question, is my SigmaXL automatically updated to include the new changes? For that, if you have version 9 installed, then version 9 includes the new changes. If you have version 8, you need to upgrade to version 9. Okay, so I have not seen a Qsum chart before. Could you explain why there are points above and below the midline? Okay, so let me go back to the Qsum slide. So basically, it's actually 2 charts. One is you're basically detecting a positive shift and a negative shift. And so if the shift in the mean is above the target, you will rapidly accumulate on the upper chart. And if the shift is below the target, it will rapidly show up on the lower chart. So in this case, because we had a shift that was a positive shift or above the target, the upper Qsum chart triggers. Had the shift been a negative, then that would have shown up on the lower chart. So it is a little bit confusing. It's not like a regular control chart. There really are 2 charts going on here, but just graphically they're put together as into a single chart. So it just depends on the direction of the shift that will determine which chart kicks in to detect. So the next webinar will be November the 12th. That's time series forecasting. So these are part 2 of 3. The second webinar will be time series forecasting. And then the third webinar will be control charts for autocorrelated data. And with that, I guess we'll call it a wrap. And I thank you very much for your participation. And I look forward to seeing you on the second webinar on November the 12th. If you need to update, please contact support at SigmaXL or info at SigmaXL, and they will take care of you for the updates to make sure you have version 9. So thank you very much.